All right, so let's continue with correlational research designs, and we'll talk a little bit about descriptive statistics as well. Again, preparing you for your course on statistics and experimental, it's important to understand descriptive statistics and inferential statistics. So we'll go there. All right. So let's just start with learning objectives. So the first thing we're going to talk about are the various ways to describe results, which are to describe group percentages, correlating scores, and means, and comparing means. We'll talk about what a frequency distribution is. We'll talk about the concept of central tendency and variability, and we'll go from there. Now, this should be a recap or review from lectures 4 and 5. Now, we said that there were 4 scales of measurement, and we said that the abbreviation or mnemonic for the 4 scales of measurement are NOIR, N-O-I-R. So that'll help you when trying to remember the different scales. So N stands for nominal. Nominal means in name only. So when we talk about nominal differences, we're talking about categorical differences. There's no greater or less than, it's just more frequently occurring or less frequently occurring. Now, when analyzing nominal data, we get to compare the likelihood of a given score occurring. So the frequency of it occurring. All right, but in reality, it doesn't tell you better or worse then. So for example, if we were going to study statistics of basketball players, and I were to ask you, in general, which is better, a center or a guard, you would probably look at me, if you follow sports, and be confused by the question, because a center or a guard is a position. And in fact, you actually need each of those positions to be successful on the basketball court. So you wouldn't be able to determine which is better. You would just be able to determine which is more frequently occurring and less frequently occurring, in which you would discover there are 2 guards and 1 center typically on the court at a given time for a team. So, but it, as I said, if you had Shaquille O'Neal versus some other guard, the center would be better, right? Because it's the person specific. Whereas if you had Michael Jordan versus some other guard, likely Michael Jordan would be better. All right. So these differences are categorical or in name only. So nominal variables include gender, ethnicity, political party, and so forth, right? So there's no objective better or worse. It's just categorically different. So moving forward to ordinal data, think terms of putting things in rank order. So you can, in ordinal data, determine better than or worse than, highest score versus lowest score. The biggest problem with ordinal data is that the units of measure are not equivalent. So for example, if you went to a swim meet and you discovered that one person got the gold medal, next person got a silver medal, and the next person got the bronze medal in that tournament, we would know that the person who got the gold medal did better than the silver medalist, and the silver medalist did better than the bronze medalist. But the question becomes, well, how much better? How long of a difference or was there between the person who came in first place, second place, and third place? And then the second question is is that difference equal across the board? And what you would find is that that difference is not equivalent. So the biggest challenge with ordinal data is that the units of measure are not equivalent. Move us to interval data. When we have interval data, we have better than, worse than, greater than, less than. But now with interval data, you have equal units of measure. So now we can make these comparisons. The biggest challenge with interval data is that there's no absolute zero. Versus ratio data, there is an absolute zero. So let's take an example of interval data. When we talk about interval data, something like temperature would be a good example. Because when we talk about temperature, each unit of temperature is equivalent, but zero doesn't always mean zero. For example, if you've ever heard of the term in the winter, sub-zero temperatures, if zero meant the absence of temperature or no temperature, it would be impossible to have sub-zero temperatures. So whether we're looking at Fahrenheit or Celsius scales, zero does not mean the absence of temperature. Versus ratio, there is an objective zero. So if I give you a test and you get every question on the test wrong, well, that's an absolute zero. So zero meant you got nothing right. So you see the differences. So let me go through the four one more time. Nominal data are just categorical differences, no better than, worse than, no greater than, less than, just more frequently occurring or less frequently occurring. Ordinal data, we could put people in the rank order, but we don't have equal units of measure. Interval data, we now have equal units of measure, but we don't have an absolute zero. And then ratio data, we have an absolute zero. Now, give me 1 second. I do want to say something to prepare you for when you're working with SPSS. When you're working with SPSS and you're coding variables, they're going to give you an option for nominal, ordinal, or scale, which is a different lingo than what I'm teaching you here. However, interval and ratio data, because they have equal units of measure, are scale data. So don't be alarmed if you don't see in SPSS the term interval or ratio. All right. So how do we analyze the results of research investigations? When describing our results, when we talk about descriptive statistics, we're providing a summary of the data rather than an interpretation of the data. So when we describe the results, we can describe the results comparing group percentages. Now, that is the most commonly occurring process for nominal data or categorical data. So we would describe or compare group percentages for nominal data. We could correlate individual scores, and that typically is used when you don't have distinct groups of subjects. And I'm going to talk a little bit about correlation at the second half of this lecture. Or we could compare group means. Group means, comparing the averages, that's used for interval and ratio scales of measurement. All right. So let's also talk about pictorial representations of data. So when we have pictorial representations, you could demonstrate the relative appearance or describe the data using frequency distributions. And what is a frequency distribution? It tells you how many times the given score occurred. And that can occur in a pie chart or a bar graph. A pie chart is exactly what it sounds like, where it's a circular pie, circle which is divided like a pizza pie or slices of a pie. And it just gives you the number of times something occurred or the percentage of the whole. And this display, this kind of display is very common when working with business magazines, newspapers, and so forth. The other way to do it is to do it as a bar graph. Now, I'm going to make a distinction between bar graphs and histograms. We'll get there. But a bar graph, you have distinct bars or separate bars to reflect each of the different scores. And then on the y-axis, you have the frequency of that score. So here's an example of a pie chart. So this particular pie chart gives you percentage. So if you were to ask people whether they like going on vacation, you might get 70% of people who say they like going on vacation, 30% who don't. Now notice it's a circle and it's cut out into like versus dislike. Is there anything better or worse about a person who likes going on vacation relative to a person who dislikes going on vacation? The answer is no. All we know is that of this survey, the respondents, 7 out of every 10 liked going on vacation. Here is another example of a bar graph. So now, again, on the y-axis, you have the frequency. On the x-axis, you have the category. And 70 participants said they liked to travel. 30 participants said they didn't like to travel. Now, frequency polygons and histograms are used specifically for interval and ratio data. So a frequency polygon is a line graph, and a line graph with continuous data, so that's why the line gets connected. Or a histogram, which is a bar graph where the bars touch because it tells the stories, because it's a continuous series on the x-axis. So an example of this would be scores on a measure of aggression. So if we ask people to, fill out a survey on aggression, well, we know that people who scored 2 on aggression for the scale is 1 point higher than 1, and 3 is 1 point higher than 2, and each unit of measure is 1 point. And so we have equal units of measure, and it's continuous. Now, and then on the y-axis is how many people rated it that way. So in this case, you might have modeling of aggression versus no modeling of aggression. And what we see is that the scores on aggression are higher on average for people who observed models of aggression versus people who didn't see aggressive acts. Now, if you look at this is a histogram. It's the same thing as a line graph or frequency polygon. The only difference is instead of it being a line, it's a bar. Now, if you look at the line graph, you will see score for number 3, score for number 4, 5. Look in the model group. Believe it or not, it's the same data as the model group for aggression, and the frequency polygon is here. So if you were to trace it along and make a line, you would see it would make the same shape of 3, 4, 5, 6, and 7 on that scale. All right. But the difference between a bar graph and a histogram, actually there are 2 differences. One is that the bars touch on a histogram, whereas in a bar graph they do not touch. And 2, with a bar graph, you're dealing with nominal data, and a histogram, you're dealing with interval and ratio data. All right. So the next thing we talk about are statistics, right? descriptive statistics versus inferential statistics. In this particular lesson, we're going to talk about descriptive statistics. And in next lesson, we're going to talk about inferential statistics. So, what are descriptive statistics? Descriptive statistics summarize or describe the distribution, and they typically have measures of central tendency, measures of variability, and correlations. So when we talk about measures of central tendency, we're looking at how scores come together at the center, whereas measures of variability, we're looking at the spread of scores apart from one another. And then correlations, we're looking at the association between the factors. So the three measures of central tendency are mean, median, and mode. And I'm sure in a basic statistics class or basic mathematics class, you probably have heard the term mean, median, and mode. And I'm actually going to go in opposite order to match the scales of measurement. The mode is the most frequently occurring score, and the mode is typically used for nominal data, because with the mode, you count frequencies, and you can count this category had more number of people in it than this category. So if we did a survey for psychology majors, you would find that there are more females in psychology than males. But that does not mean that females are objectively better than males or vice versa. It just means that they're more frequently occurring. So the mode would be the measure of central tendency for nominal data. Then we have the median. The median is the midpoint or the 50th percentile. The median is typically used for ordinal data, because what you have to do to get the median is you put the numbers from highest to lowest and you find the midpoint. Now, there is a more mathematical way of doing this called percentile point formulas, but for the time being, you just rank order from highest to lowest, which that would be ordinal data. And then the mean is the average. So you add up all the scores and divide by the total number of participants, and that becomes your average. And this is typically used for interval and ratio data. So now notice nominal, ordinal, interval, ratio. In general, we tend to say that the average, the mean, is the strongest measure of central tendency. However, with one exception. If you have a select few of extremely large or extremely small scores, that's going to shift the average or skew the average to the left or to the right. So when you have a skewed distribution or outliers, then the median becomes the measure you use. Things like average household income are not useful because there are people who are billionaires and they're going to bring the average household up. So therefore, typically when you read good journals, they'll say the median household income because they're finding that midpoint of income in America. Same thing with house or property value. Median property value is much more useful than mean property value. And here are just the ways you would calculate it. So if you look on the right, let's say you had 1 plus 3 plus 8 plus 8 plus 10, so you had 5 scores, right? If you wanted to get the average, you would add up the 5 scores and then divide by 5, so the mean would be 6. The median would be, if there are 5 scores, the third score, which is 8, and the mode would be 8. Now, in a perfectly symmetrical distribution, if you have a bell curve, a normal distribution, the mean, the median, and the mode should all be the same. Now, do we have it perfectly identical? No. But the more difference there is between the mean and the median, then the more likely you're going to have a skewed distribution. So be mindful of that. So we talked about measures of central tendency, or how scores come together to a middle of the distribution, but we also have measures of variability, which looks at how scores spread apart from one another, right? So measures of variability are also known as measures of dispersion. And the common three descriptors that you might hear for variability is the range, variance, and standard deviation. Now, the range is similar to the mode. It's the weakest measure in its category. The range is a very superficial descriptor of spread of scores. So by concept, the range is the difference between the highest score and the lowest score. Variance and standard deviation, which are used for interval and ratio data, they're a little bit more sophisticated because both of them look at the average variability in a data set. Now, I'm going to define them, and I'm going to tell you to underline certain words as I go through it. Variance is the average variability in a data set in squared deviation units from the mean. So underline squared deviation units, because variance is always the squared value, whereas standard deviation is the average variability in a data set from the mean in actual units. So underline actual units. Now, you will learn in statistics why we start with variance to calculate standard deviation. But for the time being, all you need to know is that variance is squared units, standard deviation is actual units. Now, formulaically, the standard deviation is the square root of the variance. So we undo the squared value by taking its squared root. So let's say, and let me make an application of this. Let's say you hired a psychologist to do a psychological evaluation to do intelligence testing with your child. And they do it. And you pay $400, $500 for this psychological assessment. And then they come back to you speaking jargon like this. Oh, your child is gifted. Your child scored 144 squared units above the mean. As a layperson, as a non-psychologist, you're going to be like, what does that mean? Well, if you do 144 and you take the square root of that, you would get 12. And that would be 12 IQ points. So if I said, oh, your child had 12 IQ points above the average, that would mean the average is 100 plus 12. Your child scored on this IQ test 112. So if your child has an IQ of 112. So that would mean your child is high average and probably will excel in many different things. But for you, how did we get to the point of 112? Well, we had 144 squared units above the mean. So we took the square root of 144 to get 12, and then we added it to the IQ's average of 100. But notice that's how we do it. So we have to undo the squared value to bring it back to actual units for standard deviation. Now, in order to prepare you for correlation, I want to remind you of what we talked about. Typically, when we graph, we put the independent variable on the x-axis, we put the dependent variable on the y-axis. But be very careful about deception, because a lot of marketers will change the unit of measure on the y-axis to make things look more impressive than they really are. So pay attention to the y-axis because that shows sensitivity. Now, so that when it comes to correlation, though, you are not manipulating any independent variable. So what goes on the x-axis? What goes on the y-axis? Well, for correlation, you're looking for the relationship or association between two or more dependent variables. So on the x-axis would be dependent variable 1, and on the y-axis would be dependent variable 2. So now let's talk about correlation coefficient. A correlation coefficient describes the relative strength and direction of the relationship. It has two parts. It has the sign, and then it has the actual decimal points. When we talk about the sign, correlations come in the form of positive correlation, negative correlation, or no correlation. Those are the three types of correlation: positive, negative, or no correlation. And the strength of the relationship comes between 0, which is no relationship whatsoever, to the absolute value of 1. Now, when I say to the absolute value of 1, I'm saying that for a reason, because the sign only tells you the direction of the relationship, whereas the number tells you the strength. And the closest you get to 1 in any direction, whether it be positive 1 or negative 1, the stronger the correlation is. So if you have 1.0 or negative 1.0, it's equal in terms of the strength of the correlation, because whether it's positive or negative is immaterial. So when we talk about positive correlations, a positive correlation, I'm going to remind you, I think we talked about this earlier in the semester too, but I'm going to define it again. A positive correlation is when the factors, both factors, go in the same direction. What do I mean by that? As factor A increases, factor B increases, or as factor A decreases, factor B decreases. Notice both are either increasing or decreasing together. A negative correlation is also referred to as an inverse relationship. So as one increases, the other decreases. So they're going in opposite directions, unlike positive correlation. All right. So now correlations have incredible value. So we use correlations in developmental psychology. We use correlations in a whole host of places. But if you want to know the relative role of heredity, you're going to use kinship studies and heritability estimates. A kinship study is comparing family members, identical twins versus fraternal twins, twins versus non-twins, biological relatives versus adoptive relatives. That would be kinship studies. And we report it as a correlation between 0 and 1. Now, concordance rates is actual whole number percentages, going from 0% to 100%. And concordance rates are typically used to describe psychological factors, emotional issues, psychological disorders, and so forth. So if we were to do this, a heritability estimate, if we look at Bouchard and McGew, you would see the relationship between heredity and IQ. Identical twins had a correlation of 0.86, very strong correlation. But it drops as the genetic similarity drops as well. So fraternal twins, it's only 0.6. And then when you have non-twin siblings and you introduce the environment, whether they're raised together or raised apart, it drops even further. So that shows the role of nature and nurture. So that's a heritability estimate. and here's a concordance rate. So now we're, instead of looking at correlation numbers, we're looking at whole percentages. And we're still looking at heritability, but as a concordance rate. So this is the likelihood of another twin having it if one twin has it. And most people say, oh, schizophrenia is genetic, but there are a lot of psychological disorders that have greater concordance rates than schizophrenia, such as depression, antisocial personality disorder, and so forth, where you see with identical twins and antisocial personality disorder. Now, antisocial personality disorder is a person who has sociopathic tendencies, right? If one twin has it, it's almost a 90% likelihood of the other one demonstrating antisocial behavior and criminality. So, but now let's go back to correlations. We use scatter plots, and remember that quadrant where it went down and across? We put dots in there. And the scatter plot will help you visualize correlations. And if you had a perfect correlation, a single straight line should be able to connect all the dots. So here's a perfect positive correlation, which is, notice it's sloped upward to the right. And then the other one is a perfect negative correlation, sloped downward to the right. Both cases, you can connect with a single straight line. But in reality, perfect correlations are rare. Most of the time we have correlations, but they're less than perfect. So if you have on the top left a positive correlation of positive 0.645, notice the dots cannot be connected with a single straight line, but you can see a general trend sloped upward to the right still. If you look at the right side of the graph, the negative relationship, negative 0.774, is sloped downward to the right. Again, you can't connect all the dots with a single straight line. But notice the trend, upward to the right versus downward to the right. And then no relationship is sort of like a flat line across, and it's all over the place. Now, I didn't define no relationship the same way I did. Positive relationship, I said as factor A increases, factor B increases, or as factor A decreases, factor B decreases. That was positive. For negative relationship, as factor A increases, factor B always decreases. So they're going in opposite directions. So how would I verbally describe no relationship? Listen to how I say it. As factor A increases, factor B both increases and decreases in a non-systematic way. No, in other words, the dots are all over the place. Now, it's important that I said in a non-systematic way, because there's also something called a curvilinear relationship, which is as factor A increases, factor B both increases and decreases in a systematic way. But linear correlations, linear, that's if you have two data points, always either it's a positive correlation, a negative correlation, or no relationship. So the problem with Pearson correlations is that they don't detect curvilinear functions. It's either positive or negative. That's a problem, because if we look at this scatter plot, you could see the dots are going up and then down in a systematic way. The other thing you have to be careful with is if you use a restricted range, that is a subset of the whole group, the correlation is going to drop considerably. It's going to drop because it doesn't have the full spread of scores. So when you take a little chunk out of the data set, it's going to look worse than it really is. So be mindful of restriction of range when you take a subsection of very similar scores relative to the whole scatter plot. and be mindful of curvilinear functions. One thing that's really, really important when we look at statistics is something called an effect size. An effect size is the relative strength of association between variables. And how do we get effect size? For a correlation, we multiply the value of the correlation by itself, and that becomes its effect size. It's oftentimes referred to as R square in this case. So if we were to look at effect size, a small effect is 0.15 or lower. Medium goes anywhere from 15 to 30, 0.30. And then a large effect size, 0.30 to 0.4, or anything above 0.4. But to explain variance, right, so the squared value of the coefficient, if you want to know the percentage, you do R squared times 100, that's going to have how much of variable A is accounted by B. So let's do this. So imagine you were trying to look at the factors that impact one's weight, and you ran a correlation between gender and weight. You would find 0.7. It's a strong correlation. Then if you wanted to have explained variance, you would multiply 0.7 times 0.7, which would give you 0.49, then multiply that by 100. 0.49 times 100 would be 49. That would say 49% of the variability in weight can be explained by gender alone. Now that is tremendous. You usually don't get about half of anything explained by something else. So that would be massive. But what that would also mean is that even in that strong correlation of 0.7, 51% of the variability of weight is still unaccounted for. So other factors might explain that other 51%, things like stress, exercise, diet, and so forth. And the goal would be to figure out, well, what factors explain a given outcome? And we need regression analyses for that purpose. So let's talk a little bit about regression equations. So a regression equation is a calculation that's used to predict a person's score on one variable when that person's score on another variable is already known. So you might see y prime equals a plus bx, right? This is a simplified formula. So let's say we wanted to see proximity to the teacher and test scores. So do people who sit closer to the teacher score better on a test? Well, here would be a situation. So let's say we knew that the highest score you could possibly get on this test was a 99. So A would be 99. And let's say we knew that each row that you go back, you lose 8 points on your test. Well, what would, if you had to predict, a regression equation is to predict an outcome. If you had to guess the average score of the second row, you could do 99 plus -2, right? Pardon me, 2 for second row times -8. 2 times -8 is -16. So 99 minus 16, you would predict that second row, the average score was an 83. But it's interesting, a regression allows you to predict an outcome. And that goes back to something we said in lecture 1, that correlations in its most sophisticated form allow you to predict an outcome. And the way we do it is with regression equations. Now, what we also said just a minute ago, though, was that it's very rare that a single factor can explain everything. So you might want to use something called a multiple regression analysis. So you're adding more predictor variables. So let's say we wanted to predict your success in graduate school. And we had one thing what thing do you think predicts graduate school the most? Believe it or not, it's your undergraduate grades, because past behavior is the best predictor of future behavior. But if we were to correlate your past grades, your undergraduate grades for graduate school, it would predict a certain degree. There would be a certain correlation. But if we added other factors, our ability to predict would get better. So if we add your GRE scores or your GRE subject scores, your letters of recommendation, and we added these 4 things, now we're going to be able to predict even better than your undergraduate grades alone. Now, the symbol for a single regression, a basic single regression equation, was a lowercase r. When you have multiple regression, it's going to be a capital R symbol. And when you have explained variance for a multiple regression, it's capital R square. So if we go back, you will notice we talked about squared value of the coefficient R. Well, that was for regression, but if you have multiple regression, it's capital R square. So in general, the more predictor variables you have, the more accurate of a prediction you give on the outcomes variable. Now, the biggest problem we have with correlation is that correlation does not demonstrate causation. And we said that in lecture 1. We said that in lecture 4. We said that in lecture 8 when we talked about cause and effect for experiments. So a correlation can allow you to predict an outcome, but it cannot determine cause and effect. And the biggest reason why a correlation cannot determine cause and effect is something called confounds or confounding variables. You may hear it referred to as a third variable problem. What do I mean by that? There's an infinite number of outside forces that could impact this correlation. There could be so many outside factors that impact or explain this correlation. Let me demonstrate. Low self-esteem is linked to depression, right? And we have a temporal precedence problem with this, and we have a third variable problem with this. The temporal precedence problem is as follows. Is it the low self-esteem that led to depression? Maybe. Or is it that the depression led to low self-esteem? Maybe. So we don't know which one came first. But are there outside factors that could cause both low self-esteem and depression? The answer is yes. Things like trauma. A trauma could lead to low self-esteem. A trauma could lead to depression. So it's very, very important to know that with correlation, you have a problem with these outside factors. But just because you can't demonstrate causation doesn't mean that you can't measure the effect of outside factors. There's a statistical procedure called a partial correlation, which is a fancy way of saying we're partialing out or separating out the effect of the third variable relative to the original correlation. So if that third variable is strongly linked to the original 2 factors, well, that original correlation will fall away. But if that third variable is weakly linked, then that original correlation stays intact. Let me demonstrate what I mean. So suppose we found a correlation between crowding and test performance. A negative 0.5 correlation, that's a moderate correlation. Are there other factors that could impact crowding and performance? One potential confound is social class. So financial means, right? So let's assume on the left graphic, which makes a triangle of social class, the correlation between social class and crowding was negative 0.6. That is, as social class increases, crowding decreases. And the correlation between social class and performance was positive 0.75. As social class increases, performance increases. That makes a lot of sense, right? The more money you have, the bigger the house is going to be. You might be able to afford private school rather than public school, get more individualized attention. So that's going to be less crowded. And then social class and performance, you might be able to hire a tutor and so forth. You might have enrichment activities, so many things that could improve performance. But if you look at these numbers, negative 0.6 and positive 0.75, that becomes very important because that third factor of social class is very strongly linked to the original correlation. So when we partial out social class, look at the bottom of the left side. The original correlation, which was 0.50, drops to 0.09. Went from a moderate correlation to a weak correlation when we partialed out the effective social class. Now we put the same model together, but in this case, social class, we wanted it to be weakly linked to crowding and performance. So if we have a social class linked at negative 0.10 and social class linked to performance at 0.15, so social class is weakly linked to the other two, and we partial out the effective social class, the original correlation drops, but it drops from negative 0.5 to negative 0.49. So it really doesn't have that much of an effect in that case. So that's important to know, that we have a way of partialing out potential third variables. We can't eliminate that confound, but we can measure the effect of the confound if we have the data. And that, I believe, I think I may have had a little bit more on that. So let me go back in, sorry. All right. So we have two more slides. So we have structural models and path analysis. So what is a structural model? So a structural equation modeling is an expected pattern of a relationship between variables. It's more of a hypothetical. It's based on theory. So we look at what's in the research. We say we expect these factors to be linked. And then path analysis is a mathematical process. So let's put it all together. So what you're looking at here, the arrows is the model itself, and the path analysis are the correlations linked. So this study was published in 1998, and it looked at attitudes, gender role attitudes, career orientation, and career behavior. So in this, they took women and they measured their relative attitude. So women could have a traditional attitude towards their role in society, or they could have a different attitude towards their role in society. Now, what's nice about this is that there was a change from women being at home to women being in the workforce. So there was a shift in society. And then we looked at, people you value in your life, whether it be your parent or your romantic partner, and their attitudes towards traditional roles. What's interesting is that your career orientation in 1973, so they followed them for some time, right, was more influenced in 1973 by the perspective of one's parent or boyfriend than their own gender attitude. So that there's a correlation between perceived boyfriend or parent preference and career orientation 0.5 versus gender role, which was 0.2. Now, the good news, though, is if you follow people 15 years later in their career behavior, the relationship between career orientation and career behavior is 0.3. So it's relatively weak of a correlation 15 years later. But now it's interesting, right? This is a longitudinal study, and they measured this structural equation model, right? So they had the different factors. They thought gender role, attitude, perceived boyfriend parent preference, and career orientation were all linked. All three of those came together to predict career behavior. And then in the end, they found that in the moment it had an impact, but long term it did not. And so the path analysis are the correlations by the arrows. So I will stop there, and that is lecture 12. So let's stop my share. Okay. And I'm going to end the recording there, and we'll talk about inferential statistics next week. Take care.